Welcome to the deep dive. Today, we're really getting into the nuts and bolts of how buildings actually stand up.
Yeah, we're looking at the practical side, the things that make construction work day to day.
We've gathered some great info that honestly breaks down some pretty complex stuff into something understandable.
It covers quite a range, doesn't it?
Yeah.
From basic math to the actual order things get built in, even, the materials themselves.
Exactly. We think you'll find some maybe surprising details about how it all comes together.
Definitely. It's about understanding the fundamentals, the core knowledge behind it all.
So let's dive right in. First up, water tanks, specifically cylindrical ones.
Right. A common thing you might need to build or install.
So imagine you have one with a diameter of 1.2 meters. How do you figure out the distance around its base? The circumference.
Okay, yeah, that's a classic geometry problem. Use the formula. Circumference equals 2 times pi times the radius.
Pi, right, about 3.14. And the radius.
Well, they gave us the diameter, 1.2 meters. The radius is just half of that.
So 0.6 meters. Simple enough.
Exactly. So you plug that 0.6 meters into the formula, 2 times pi times 0.6.
Which gives us, carry the one?
It comes out to about 3.77 meters.
Okay, 3.77 meters around. Why is knowing that specific number so important in practice?
Well, imagine you're building a base for it, or maybe putting insulation around it. You need that exact measurement if you get it wrong.
Everything else is off.
Pretty much.
Yeah.
Costs go up, delays happen. It seems small, but it matters.
I can see that. Okay, so that's the distance around. What about how much it holds, the volume?
Ah, yes, volume, also
Yeah.
critical. For a cylinder, the volume is pi times the radius squared times the height.
We know the radius is 0.6 meters. Let's say the height is 1.8 meters.
Right, so first square the radius.
Yeah.
0.6 times 0.6.
That's 0.36.
Yep, 0.36 square meters.
Here.
Then multiply that by pi, and then by the height, 1.8 meters.
Okay, crunching those numbers.
You end up with roughly 2.04 cubic meters.
2.04 cubic meters. And knowing that volume is key for...
Water supply, planning usage, you absolutely need to know the capacity.
Makes perfect sense. So these calculations aren't just school math, they're fundamental building blocks.
Couldn't have put it better myself.
All right, let's shift gears. Let's talk about the main parts of a building people recognize. Floor, foundation, roof. What are their core jobs?
Okay, the floor, pretty obvious in one way, right? It's the flat bit you walk on.
Stable, level surface, supports furniture, people, activities.
Exactly. But it also has to be durable, take a lot of wear.
Sure. Then the foundation. Mostly hidden, but vital.
Utterly vital. Its main function is transferring all the weight, the entire building's load, safely down into the ground.
Spreading it out.
Spreading it out, yes, but also anchoring the building.
Mm.
Resisting movement, wind, even earthquakes to some extent. A bad foundation, well, that causes huge problems. Cracks, instability.
The unseen hero, then.
Sort of, yeah. And then the roof. More than just keeping rain out.
Definitely. Protection from weather is primary, of course. Rain, snow, sun.
But also insulation, right? Keeping heat in or out.
Yes, a huge part of energy efficiency. And providing that overall shelter, creating the controlled environment inside.
So all crucial elements.
But they don't just appear. There's an order, a sequence to construction.
A logical flow, yeah. Typically, you've got about 6 main stages.
Okay, what's first?
You start with excavation, digging the hole, basically.
The foundation.
Makes sense. Then comes the foundation itself, pouring the concrete, creating that base.
Got it.
Stage 3.
The substructure. This is often block work that sits on the foundation and raises the building up slightly from the ground.
Ah, okay. Protection from damp, maybe.
Exactly. Then you lay a floor slab, usually the ground floor.
Step 5 must be walls.
Yep. Walls go up, defining the space.
And finally,
The roof. Put the lid on it, so to speak. That's the basic sequence.
that really clarifies the overall process.
Yeah.
Let's look closer at that foundation and substructure. We heard about pad foundations.
Right. A pad foundation is like a square or rectangular concrete slab, usually placed under a column or a concentrated load point, instead of a continuous strip.
Sometimes, yeah. It just spreads that specific load over a wider area of soil. And the substructure, often blockwork, sits on these pads,
And its job, again, is...
raising the floor level above the ground, keeping moisture out, and further distributing the load onto those pads.
support and protection. Now, this surprised me using Pythagoras' theorem in foundation work.
Oh, absolutely. It's a builder's best friend for getting perfect right angles. The classic A plus B is C par.
How does that work on site?
You use the 3-4-5 ratio, or multiples of it. So you measure 6 meters along one line from a corner that's your A, but multiplied by 2.
Okay.
Then you measure 8 meters along the other line from the corner that's b times 2.
Right, 6 and 8,
If the diagonal distance between those 2 points, the hypotenuse C, measures exactly 10 meters,
which is 5 times 2.
then you know you have a perfect 90-degree corner.
Mm-hmm.
It's crucial for making sure the building is square from the very start.
Wow, so simple yet so effective.
Yeah.
Okay, let's move inside the building. Stairs. Timber stairs have lots of parts with specific names.
They certainly do. Let's break it down. You have the newel post. That's the main vertical post, usually at the start and or turns. Supports the handrail.
Got it. The uprights along the side.
Those are balusters, or sometimes called spindles. They fill the gap between the handrail and the steps for safety.
And the part you step on.
That's the tread, the vertical bit between the treads.
That's the riser.
Correct. What you hold on to is the handrail.
Obvious enough.
And the whole safety barrier system, handrail plus balusters, is often called the guardrail or balustrade.
Okay, clear. Now, what if you add a landing? That flat platform partway up.
Good question. A landing breaks the flight of stairs into 2 runs.
So you go up, hit the landing, turn, go up again?
Usually, yes. So the handrail needs to follow that path, continuing along both flights and around the landing edge. Often needs special joints or bends.
And the baluster.
Same deal. They need to continue along both runs and protect the open edge of the landing.
What about the main support beam on the side, the stringer?
The stringer, which holds the treads and risers, would typically either be cut to meet the landing structure, or you might have separate stringers for each flight connecting to the landing. It just needs to be structurally sound.
Right, it all has to connect logically and safely. Okay, let's picture a basic brick wall sketch, maybe unfinished. What if we need to add a door and, say, 2 windows?
Okay, the key thing when you make an opening in a masonry wall is the lintel.
The beam across the top.
Exactly. It's a horizontal support. Could be concrete, steel, even timber sometimes that sits above the opening. Its job is crucial. It carries the load of the wall above the opening.
So the bricks don't just fall down into the doorway or window space.
Precisely. So on your sketch, you draw a lintel spanning across the top of the proposed door opening and one across the top of each window opening.
So 1 door lintel, 2 window lintels, what else?
For the door, you'd also show the blockwork or brickwork being completed above the lintel, up to the top of the wall. For the windows, the space below the lintel is left open for the window unit itself.
Got it. The lintel makes the opening possible. Now let's get really hands-on. Laying a single concrete block. What's the process?
It's a methodical sequence. You need to get each step right. First, wet the area where the block is going.
Why wet it?
Helps the mortar bond better, stops the dry block sucking all the moisture out too quickly. You might use a watering can or just a wet brush.
Okay. Step 2.
Spread the mortar. Get a nice even bed of mortar on the surface below using a trowel.
Then place the block.
Carefully, yes. Place the block onto the mortar bed. Use your hands, probably with gloves.
And just leave it.
Oh no. Step 4. Tap and level. Use a rubber mallet to gently tap the block down into the mortar until it's at the right height and level.
How do you check level?
That's step 5. Check alignment. Use a spirit level on top and along the side to make sure it's perfectly horizontal and vertical.
Crucial for a straight wall.
Absolutely. And finally, step 6. Fill the joints. Use more mortar to fill the vertical gap between the new block and the one beside it. Smooth it off with a pointing trowel.
Seems straightforward, but I bet there's a knack to it. What about the concrete itself, say for something structural like a ring beam? Is there a standard mix?
There often is. A common mix for things like ring beams is 1.2.4.
Meaning?
1 part cement, 2 parts sand, and 4 parts gravel or crushed stone, all measured by volume.
Why that specific ratio?
It provides a good balance of strength, workability, and economy. You get enough cement to bind everything strongly, enough sand to fill the gaps, and the gravel provides the main bulk and compressive strength.
So if you think of it as fractions, cement is 17th, sand 27th, gravel 47th.
Exactly. That ratio works well for many applications.
Okay, you've mixed and poured the concrete. It just hardens then.
Not quite. It needs to cure properly to reach its full potential strength. Curing is vital.
And how do you cure it?
It's all about maintaining moisture and temperature. 2 main ways. Water curing, which means keeping the surface constantly wet, maybe by ponding water on top or spraying it. Or sealed curing, where you cover the concrete with something like wet burlap sacks or plastic sheeting to trap the moisture already in the mix and prevent evaporation.
Why is stopping evaporation so important?
The chemical reaction between cement and water, called hydration, is what gives concrete its strength. That reaction needs water. If the water evaporates too quickly, the reaction stops prematurely, and the concrete won't be as strong or durable.
I see. And is there a way to test the concrete mix before it sets to see if it's right?
Yes, a very common site test is the slump test.
Slump test, what does that involve?
You take a standard metal cone, open at both ends, fill it with fresh concrete in layers, rotting each layer. Then you carefully lift the cone off.
And the concrete sumps.
Exactly.
Yeah.
You measure how much the pile of concrete drops or slumps from the original height of the cone.
What does that tell you?
It indicates the consistency or workability of the mix. Too little slumps means it's probably too stiff to place and compact properly. Too much slump means it might be too wet, which could lead to lower strength.
So it's a quick check on consistency. Interesting. Now, going back to mortar, the stuff between the blocks, what does the cement actually do in there?
The cement is the binder. It's the active ingredient. When you mix cement, sand, and water, the cement undergoes that hydration reaction we mentioned.
The chemical hardening process.
Right. And as it hardens, it coats the sand particles and binds them together. And crucially, it adheres strongly to the surfaces of the blocks or bricks. That's what gives the mortar its strength and makes the wall a solid unit.
The glue, essentially.
A very strong chemically active glue, yes.
Okay, final practical bit. Mixing concrete by hand. No cement mixer available. How's it done?
It's hard work, but doable. You need a systematic approach. First, prep your surface. It needs to be clean and hard, a mixing board, wheelbarrow, or even just clean pavement.
Then the ingredients.
Measure the dry stuff, cement, sand, gravel, using your chosen ratio, maybe with buckets or a measuring box for accuracy.
Just pile it up.
Pile it up. Then step 3. Mix the dry ingredients thoroughly. Use a shovel, turn it over and over until color is completely uniform. No streaks of cement or sand.
Okay, dry mix ready. Now water.
Step 4. Form a crater in the middle of the dry pile, like a little volcano.
Great.
Step 5. Gradually add water into the crater. Don't dump it all in at once.
And start mixing.
Yes. Step 6. Continuous mixing. Start pulling the dry material from the edges into the water in the center with the shovel. Keep turning and mixing until you get a uniform, consistent mix. All the aggregate should be coated, and it should have the right workability, not too wet, not too dry. That's step 7, check workability.
And the final step.
Use it immediately. Concrete starts setting pretty quickly, especially once the water hits the cement. So mix what you can use within maybe an hour or so.
Sounds like a proper workout. What tools are essential?
You absolutely need a shovel, a good sturdy one, a wheelbarrow or mixing board for the surface, a bucket for measuring water and maybe aggregates, and ideally a measuring box if you want accurate volume ratios for the dry stuff.
Well, this has been fascinating. We've gone from calculating circumference and volume
to the sequence of building, the function of foundations, lintels.
How to lay a block, mix concrete, understand curing. It really covers the essentials.
It does. And it highlights that even seemingly simple structures rely on a surprising amount of know-how and precision.
You really do start to see buildings differently, don't you? Appreciate the thought behind them.
Absolutely. It's not just bricks and mortar, it's applied science and careful planning.
Which leads to a final thought. We talked about the precision needed for a square foundation using Pythagoras. It makes you wonder, doesn't it?
What other areas demand that same pinpoint accuracy?
Exactly. What other aspects of construction require that level of precision, and crucially, why? What happens if you're just slightly off?
That's a great question to ponder. It really underlines how critical accuracy is throughout the entire process for the final integrity of the building.
Something for you all to think about. Until our next deep dive, keep looking closely at the built world around you.